Hi, I'm Suhail, and today I'm going to present a few tools for doing private computation on health data. What I mean by private computation is actually running data analysis without sacrificing data privacy. This is a topic I've been researching with my colleagues at the University Medical Center in Freiburg, Germany. And what we've noticed is that many of the privacy tools that are used today sacrifice a lot of data accessibility and utility for only marginal gains in privacy. But recently, there has been sort of an inflection point where emerging research and tools have allowed for preserving or sometimes even increasing data privacy without sacrificing its utility. This whole talk is simply just to walk through this graph and where different data privacy tools could fall on it. Let's start right away with data anonymization, which sounds good on paper, but isn't that good in practice, where it's prone to what is called de-anonymization attacks. One such attack was demonstrated on a Netflix dataset of anonymous reviews, so reviews of shows or movies or whatnot. And researchers were able to re-identify the individual reviewers in this dataset using another dataset from the Internet Movie Database or IMDb. So anonymization, not so good. Firewalls and bureaucracy. Firewalls, pretty straightforward. What I mean by bureaucracy are things like GDPR and HIPAA, which aren't particularly bad, but actually they stand in the way of small to medium-sized research teams who cannot even think of running large-scale data analysis across multiple hospitals or multiple geographies, for instance. For bigger players, this is not so much a problem. So these are the players or companies that can find legal backdoors or loopholes. One concrete example of that is Google's Project Nightingale, which was done with an American healthcare IT provider. I think a couple of years ago, the leaks were announced. But anyway, the project entailed moving health records of millions of Americans to Google Cloud for data analysis without anyone's consent or opt-in. So regulations, firewalls, and bureaucracy, not so good. How about encryption? Also not so good. A prominent recent attack, it's almost a year now, was on a Finnish psychotherapy practice where the attackers could get a hold of the encryption keys and actually decrypt thousands of private and sensitive psychotherapy records there. So encryption doesn't do it. So far, not so good. Let's try to move past this inflection point a bit and see what we can do better. But before we do that, I just want to ask the question, why is all of this important? Why is it important to preserve data utility while preserving its privacy? Well, I think the reason is that running secure and safe data analysis at scale could actually transform medicine and public health by accelerating biomedical research. One small example of this is this convolutional neural network, which was trained to identify or diagnose Alzheimer's disease from PET scans. Now, to scale this to other diseases than AD and to more accurate models, we definitely need better tools. One such tool could be distributed learning. It's sometimes called federated learning, or in some configuration called multi-party computation. Now, the basic principle of the classical way to do machine learning is that we send the data to where the models are. So the models get the data, get trained, and then we move from there. With federated learning, the model actually goes to where the data is without the data leaving its warehouse or where it lives, especially if it's sensitive data. This is really, really advantageous in healthcare. This is an example of federated learning in healthcare where small local models are deployed to different hospitals where data resides. They're trained on this private data, and then their outputs are sent to a global or big model that basically crunches all the data from everyone. The drawback of federated learning, or one of them that has been demonstrated, is that they could leak information or the private data they've been trained on. Not all of it, but some of it. Another vulnerability is that these models could be poisoned with data that could affect the model accuracy or sometimes models' performance. All of these issues could be mitigated using split learning, which was pioneered by Vepakoma and his colleagues, but we'll come back to this later. First, let me show you differential privacy. To illustrate differential privacy, let's take this simple dataset or table of record and run it through some model, add some random noise to it, and we get some output or inference about the data. Now, with differential privacy, if we remove one record, let's say we remove John, and rerun the data through the model with the noise, we should get similar output or inference. So we can't tell who was removed from the data in whose state. This is sometimes called plausible deniability. The problem with this random noise that is added with differential privacy is that it can really and measurably impact the model accuracy, which means the model cannot scale to other data sets to do inference and whatnot. How about zero-knowledge proofs? So these are mathematical proofs that we know something without revealing what that something actually is. The perfect and simplest example of zero-knowledge proofs are passwords. So with passwords, we prove to a third party or a website that we know our password without actually revealing what the password is. Banks are also using zero-knowledge proofs to verify that the salary of a loan applicant, for instance, falls within a certain range without revealing what the salary actually is. One of the major problems with zero-knowledge proofs is that they lack, or they still lack, standardization. Probably slightly better technique is called TEAS, or Trusted Execution Environments, which are isolated hardware and software environments where only authorized applications for data analysis could run on the sensitive data stored there. The problem with these environments is that the applications should be programmed and tailored specifically to them, and that is problematic when the applications need to run cross-platforms. One last technique is homomorphic encryption, which is basically it's a mathematical trick or a mathematical technique that allows for computation on encrypted data. So models could learn from the data while it's encrypted without having to decrypt it, and they could give encrypted outputs that can only be decrypted with the encryption key holders. Now, taking this technique to practice is a bit tricky because it still requires a lot of computational power. So going through the pros and cons of these tools, we thought that there could be a slightly better tool or system that actually takes all of them into account, brings them all together into one integrated workflow or ecosystem, so that we can get the maximum data privacy and utility at the same time. Let me show you on a high level how that system could look like. Let's start with the data owner, which could be a hospital owning patient or sensitive patient data. ideally in a trusted execution environment. And this data is encrypted using multiple encryption keys. So this removes the single point of failure of single encryption keys. This means that to encrypt or to decrypt the data, we need multiple keys from multiple parties. One of them could be the patient, in order to have this data in decrypted form and then do analysis on it. So let's assume the data got decrypted using multi-sig authorization or multi-key authorization, and now the hospital forward propagates this neural network up to a certain split layer. So we're back to split learning. This is what split learning is about. Following that, there should be some minimization of distance correlation. This is a statistical technique to preserve data privacy. So this is done between the input data and the split activations. The network gets compressed afterwards just for communication efficiency, and zero knowledge proof is generated that no malicious computations were run on this network without revealing what the computations are. The split layer outputs and the zero knowledge proofs are then sent through a secure communication layer like SSL to the model owner, who's also running computations in a T, probably not. The model owner verifies the zero knowledge proof. After verification, they pick up the forward propagation from the split layer, and then they back propagate the network gradients. Following that, they do something called optimizing categorical cross entropy. This is a mouthful, but in principle, this is an optimization for the model accuracy so that we don't lose so much accuracy in the process. And this is done between the split activations and the output labels. After that, again, the network is compressed and a zero knowledge proof is generated that nothing bad happened, and the split layer gradients and the zero knowledge proofs are sent back to the data owner, who verifies the zero knowledge proof and picks up the back propagation from the split layer on, and continues in this cycle until the network is trained enough. Now, we don't think of this as a bulletproof system, but more of a Swiss knife that is equipped with multiple tools for different occasions or loopholes or vectors of attacks in case of data security. The main problem with this is that it is a theoretical one and it's not yet battle tested. The following, or the immediate next problem, would be acceptance. Would organizations and big hospitals actually agree to test such Swiss knife or such tool, or would they prefer to stay with their legacy systems? Thank you very much.